Okay, continuing with part 2 on our zeros of polynomial functions, I would like to jump into the fundamental theorem of algebra. Which says that every function defined by a polynomial of degree 1 or more has at least one complex zero. Okay. This was proven by Carl Friedrich Gauss in his doctoral thesis in 1799. At 22 years old. He's a pretty smart guy. He was only 10 when he was able to add the numbers from 1 to 100 in his head very quickly. Teacher was getting kind of annoyed by all the questions and all his antics in class. It was just because he was so smart. So she gave him what she thought was busy work, and he came back very quickly with the answer. But that's a story for another time. Or if you take my MGF 1107 class, you can hear that story in those videos. All right, so what is this basically saying? So every function defined by polynomial of degree 1 or more has a zero. So this means every such polynomial can be factored. Okay, so just a little quick rundown on kind of the mathiness of this. So let's say you have an f of x that is degree 1 or more. Then there's some case of 1 such that evaluating the function at case of 1 gives you 0. So in other words, case of 1 is a 0 of the function. So by the factor theorem that we've covered in a previous video, you can factor your function into x minus k sub 1 times q sub 1 of x, which is some polynomial to q sub 1 of x. So you can, if it has at least a degree 1 or more, then you can have a factor times a polynomial. You can factor it down into an x minus k factor times another polynomial. And then you can keep, and in that q sub 1 polynomial, you could keep breaking that one down. If it has a degree 1 or more, then you could end up breaking it further down like this. And so on and so forth until you get it all the way down to this format. The a is the leading coefficient of your polynomial. This result suggests something called the number of zeros theorem, which I'll get to in a second. I just wanted to show you some quick little examples. Like, for example, let's say your function, you have the polynomial function x plus 5. Okay, I know this is linear, but what this thing is saying is that, as long as you have a degree 1 or more, which we do, we have degree 1 here, then we can break this down. So we could break it down into 1 times x minus negative 5. The 1 is that q sub 1 of x in the definition earlier, and then the x minus negative 5 is x minus k sub 1. If you had f of x equals 2x minus 3, you could rewrite that as 2 times x minus 3 halves. So again, so this time the 2 in the front is your q sub 1 of x, and then you have your x minus k sub 1 again. So you can break it down like that. If you have f of x equals 9x squared minus 16, you might think about breaking that down into 3x plus 4, 3x minus 4, because it's a difference of squares. But according to the fundamental theorem of algebra, we can rewrite this even more differently. Where I factor out the 3's. 3 times 3 is 9. So x plus 4/3 times x minus 4/3. So the 9 is your a, or your leading coefficient. And you have your x minus k sub 1, x minus k sub 2. So do that, and that tells you what your zeros are. Your 4/3 and your negative 4/3 are your zeros. So it's saying they can all be broken down that way. So what's next? We have the number of zeros theorem. What does this say? A function defined by a polynomial of degree n has at most n distinct zeros. So let's say you have a function like f of x equals negative 1/2 x cubed plus 19 halves x plus 15. Well, this polynomial is of degree 3 because you're looking at that highest exponent there in that leading term. So we know that it has at most 3 distinct zeros. It could have 1 or 2, but that's the most. It can't have more than 3 as far as distinct zeros. And in this case, the zeros are negative 3, negative 2, and 5 for this particular example. All right, another example. Let's say you have function 3x cubed minus 36x squared plus 144x minus 192. Okay. This particular function, we're looking at that leading coefficient, so it has degree 3. At most 3 distinct zeros. fact, if you go ahead and factor this one out, it looks like this. Turns out that the 0 is 4 with multiplicity of 3. In other words, it ends up being the same number 3 times. So they say that the 0 is 4 with multiplicity of 3. Let's say you have f of x equals 5x squared times x squared minus 16 times x plus 5. Your zeros here, because you have if the x squared equals 0, so x equals 0. Technically 0 with multiplicity of 2. And then for the x squared minus 16 equals 0, that's x plus 4 times x minus 4. So you have plus or minus 4. And then for x plus 5 equals 0, you have x equals negative 5. So negative 5. We don't usually say it, but these three, have multiplicity 1. They only appear one time. Whereas the 0, 0 times x and x both come out to 0. So that's what if you see the word multiplicity, that's what's happening. All right. Let's say it asks us to go a little bit further, and let's say it asks us to find a polynomial function f of x of degree 3 with real coefficients that satisfies the following. One, that the zeros are 2, negative 3, and 5. And then 2, that f at 3 equals 6. They do not tell us anything about the leading coefficient. So that's the part we actually have to focus on solving. So we know that our functions, these polynomial functions, can be expressed in this format. And I'm just going to stop with that because I have 3 zeros, so I have 3 factors. Those are the only zeros. It doesn't say there's any multiplicity or anything. If there's multiplicity, I would need to account for that, but it doesn't say that. So I can go ahead and keep a as my leading coefficient because I don't know what that is yet. But I can write x minus 2, since one of the zeros is 2. I can write x plus 3, since one of the zeros is negative 3. And I can write x minus 5, since one of the zeros is 5. If I go ahead and multiply that out a bit, x minus 2 times x plus 3, just do some foiling. You'll get x squared plus x minus 6. That we're going to multiply with x minus 5. And then if you finish multiplying those together, you'll get x cubed minus 4x squared minus 11x plus 30. Yeah, just mentally double checking my multiplication, but yeah. All right. Now we know, again, that f at 3 is 6. So let's put that in. F at 3 is going to equal a times 3 cubed minus 4 times 3 squared minus 11 times 3 plus 30. But we're also told that that equals 6. So we can work that out a bit. we get a times negative 12 equals 6. So a equals negative 1/2. So now we know our leading coefficient. So we can go back to write this function. We can say f of x equals negative 1/2 parentheses x cubed minus 4x squared minus 11x plus 30. And then we can always distribute the 1/2 and make this all nice and tidied up. So that we have negative 1/2 x cubed plus 2x squared, plus 11/2 x minus 15. And that would be the official function. That's the official polynomial function. Nice cubic, which, works out well. It's degree 3, so it should be a cubic function. So if you're asked to come up with the function, that's how it's done. Okay. So all of this so far has had very real zeros. But what if we're dealing with the zeros that are complex, non-real? What do we do then? Like, what's going on with that? How does that work? Okay. So that's going to be a large part of the remainder of this lesson. All right, conjugate zeros theorem. If f of x defines a polynomial function having only real coefficients, so we're dealing with the coefficients being real only. You can have polynomial functions where you have coefficients that are non-real, complex non-real, but this is limited to real coefficients right now. And if z equals a plus bi is a zero of f of x, where a and b are real numbers, then the conjugate which we'll just do a little bar over it to indicate the conjugate of the complex number, a minus bi is also a zero of f of x. So this is where we're dealing with polynomial functions that have some of these. This is where it's really going to be important when we're dealing with these functions that have these non-real complex type zeros. If your polynomial function has all real coefficients, then your zeros will come in conjugate pairs. Remember, the conjugate, like if you have a plus bi, the conjugate just changes the sign in front of the b there. That's all that means. Okay. Which they do like a little proof in your book, again on this time on page 352, if you're interested in looking at it in more detail. I'll just kind of run through it real quickly. But you can prove that both z and often we'd say like z hat or something, and conjugate are zeros of the same function. But you have to have real coefficients in the polynomial. So like if you were talking about a function and you put in a z instead of an x, where that z is a zero, then you can set this equal to 0. And then if you took the conjugate of both sides, according to the properties of conjugates, which you can look in your book for those. I'm not going to go into detail reviewing properties of conjugates, but if you'd like to look in your book, you can see those. Then if you take the conjugate there of that whole function, you can also break it up. You can go down, break it up until you have a sub n conjugate z to the n plus a sub n minus 1 conjugate z to the n minus 1, all the way down to a sub 1 conjugate z plus a sub 0 equals 0. So that just, it leads to showing that the function evaluated at the conjugate also equals 0. So if you have that complex number that works as a 0, then you'll have its conjugate that also works as a 0. So, okay, now let's get to the business of actually using this. So what's that gonna do for us? Okay, so let's say that we need to find a polynomial function f of x of least degree having only real coefficients and zeros, -4 and 3 minus I. All right, the fact that we know that it has only real coefficients, then we can tell ourselves too that not only are -4 and 3 minus I zeros, but then the complex conjugate pairs theorem comes in, conjugate zeros theorem. So 3 plus I automatically has to be one of those zeros. So you can go ahead and set up factors that way. You can say x plus 4 is a factor. You can say that x minus 3 minus I is a factor. You can say x minus 3 plus I is a factor. So you have x plus 4, then let's see, x squared. I'm going to rewrite this a little bit. I'm going to say x minus 3 plus I for this one, and I'm going to say x minus 3 minus I for this one. So then it'll turn into a difference of squares. So we could say x minus 3 squared minus I squared. So that turns into x squared minus 6x plus 9. I squared is -1, so that turns into plus 1. So you have x plus 4 times x squared minus 6x plus 10. So you distribute your x, you have x cubed minus 6x squared plus 10x. Distribute your 4, you have plus 4x squared minus 24x plus 40. Combine all your like terms, you end up with x cubed minus 2x squared minus 14x plus 40. And there's your function. They did not give us any information to go any further with this. Like we don't know what the leading coefficient was supposed to be. It just said find a polynomial f of x of least degree. So, I mean, we've got the 3 zeros, so we know the least degree would be 3. So 3 distinct zeros. None of them have a multiplicity, none of them repeat. So we're going to have an x cubed situation going on here. Okay. Now, if you think about what's happening here, a polynomial function with real coefficients of odd degree in where n is greater than or equal to 1. So that's important again. The degree has to be 1 or higher. Must have at least one real zero. Because you're talking about odd degrees. So the degree is 1, 3, 5, 7, 9, numbers like that. Because remember, zeros of the form a plus bi come in conjugate pairs in this situation. Because we're talking about real coefficients. So if it's an odd degree, like if n is 1, it's just going to be 1 real zero. If n is 3, it could be 3 real zero. It's going to be, it could be 3 just like real numbers, or it could be 1 real with 2 non-real complex. So if you have an a plus bi, you have to have an a minus bi. So for odd degree, by the time you subtract the pairs, then you're going to have at least one left over. And then for even degree n, same kind of situation, but with an even degree n, may have no zeros. May have no real zeros, sorry. Because even degree, it could be all these complex conjugate pairs. You never know until you work it out and find them. So it's possible to not have any real zeros. And remember, the zeros are where the graph crosses the x-axis, but we tend to deal with xy coordinates. We're not dealing with the real versus complex plane. So on our graphs, if you don't have any real zeros, your graph's not going to cross the x-axis. You still have zeros, and if you were to graph them on the real versus complex plane, then you would see them crossing in there, but we're not dealing with that. Okay. Let's see here. Let's look at another example. What if we don't have real coefficients? Okay, let's say you have a function like 6x cubed plus 19 minus 6ix squared plus 16 minus 7ix. So you can have non-real complex coefficients. It is possible. Plus 4 minus 2i. So let me just make sure I copy that correctly from my notes here. Yes, and we know that it has a 0 at negative 2 plus I. And we want to factor into linear factors. So we want all of our factors to have at most an x to the first. No x squared, x cubed, or whatever. So we can't assume conjugate pair because of the non-real coefficients. Like 19 minus 6i, 16 minus 7i, that nice constant down there, 4 minus 2i. So we're stuck doing some division. So we can do some division. We can do some synthetic division. We can put a 6. We can put a 19 minus 6i. Just go ahead and put those coefficients in like you normally would have. 16 minus 7i, 4 minus 2i. And let's do some synthetic division using negative 2 plus I. X cubed, x squared, x, 0, so I don't need any zeros in there. I think we're good. All right, bring down the 6. Multiply 6 times negative 2 plus I, you get negative 12 plus 6i. Add those, you get 7. Multiply 7 times negative 2 plus I, and you get negative 14 plus 7i. Add those, you get 2. 2 times negative 2 plus I gives you negative 4 plus 2i. Add those, you get 0. Looking good so far. So we now have a 6x squared plus 7x plus 2 factor to go along with that lovely x minus negative 2 plus I factor, because k being negative 2 plus I. All right, what can we do with that 6x squared plus 7x plus 2? You could try to factor it, but I'm going to go ahead and use the quadratic formula to show you how that would translate. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So I have negative 7 plus or minus 1 over 12. So that gives me negative 1/2 and a negative 2/3. So if x equals negative 1/2 for one of the zeros, x plus 1/2 is 0, 2x plus 1 is 0. Just multiply by 2. If x equals negative 2/3 for one of the zeros, x plus 2/3 equals 0. Multiply through by 3, 3x plus 2 equals 0. So now we officially have that f of x can be written in the form x minus the negative 2 plus I from earlier, we were given that, times 2x plus 1 times 3x plus 2. And now it's fully factored. Woohoo! Okay, one final topic in this lesson. There is something called Descartes' rule of signs that can be very helpful. I don't know quite why they saved this to the end, because to me, it should probably be presented a little sooner, but maybe they just want you to have a good idea about what's happening first. But Descartes' rule of signs is a nice little way of trying to narrow down further when you're trying to find your zeros. Okay, so f of x is a polynomial function, again, with real coefficients. So we're back to real coefficients again. So if you have those non-real coefficients, this is not going to work. With real coefficients in a non-zero constant term. So you need a constant term down on the end there for this to work. And with terms in descending powers x. So if it's like a cubic, it needs to go from x cubed to x squared to x to constant term, something like that. It has to have real coefficients, non-zero constant term, and it needs to be written in descending order. So the number of positive real zeros of f of your function either equals the number of variations in the signs occurring occurring in the coefficients of f of x. I'm going to start abbreviating, this is a lot to write. Or is less by a positive even integer. For the negative real zeros of f, either, it's the same idea, either, but with f of negative x, either equals number of variations in sign of f of negative x, or is less by a positive even integer. They almost read identical, except with the positive real zeros, you're looking at f of x, and with the negative real zeros, you're looking at f at negative x. But you're going to look at how many times the signs vary, and that's going to tell you it's going to either be that many of those or less by a positive even integer. Okay, what the heck does that mean? All right, so let's say you have a function f of x equals negative 2x to the fourth plus 3x cubed minus 5x squared plus 4x minus 1. If you look at the signs from, like starting from the left, from term to term, we go from having a minus to a plus, so that's a variation in sign. Then we go from having a plus to a minus, that's another variation. Then from minus to plus, and then from plus to minus. So there are 4 variations here. So what does this tell us? So we have, for possible positive real zeros, number of possible positive real zeros. It's either 4 or it's less than that by 2. So it could be 4 minus 2 is 2, or minus 2 is 0. So you, like, whatever the number of variations is, and then start subtracting 2 until you get down to 1 or 0. Then we look at f of negative x, where you plug in a negative x. That would be negative 2x to the fourth minus 3x cubed minus 5x squared minus 4x minus 1. And notice that there are 0 variations. So there's 0 negative real zeros. Oops, I was trying to write in black on that one. So for this scenario, what could you have? You could have 4 positive real with 0 non-real. You could have 2 positive real, 2 non-real complex. So remember, those non-real complex have to, if you're talking about real coefficients, then they have to come in conjugate pairs. Or you could have 0 positive real with 4 non-real complex. The degree of the polynomial technically tells you how many zeros you're dealing with. It's just you might be dealing with non-real ones. So x to the fourth tells me, okay, there should be 4 zeros. Some of them might repeat, have multiplicity. Some might be non-real. It's hard to say until you start really working on it. But Descartes' rule of signs can at least give you a heads up about what to expect. So as soon as you see that, you're like, oh, so when I start trying to guess at the zeros, I know not to bother with anything negative, because there are no negative real zeros in this. So just focus on positive ones and try those, like the whole guessing and checking we did earlier. Trying to plug in or do synthetic division, trying to figure out, like, what are some of the zeros here? And that's the way we do it. All right. I'll do another function. Let's say you have f of x equals x cubed plus 2x squared plus x minus 10. Well, for f of x, there's one variation. So we know that there's one positive real zero here. But I see that x cubed, so that's interesting. So let's look at f negative x, see what's happening there, see if we have any negative real zeros. And then from there we can just deduce whether there's possibly any non-real complex zeros. So f at negative x, you have negative x cubed plus 2x squared minus x minus 10. So sign variation, there's two variations as you make your way from left to right. Remember, everything needs to be in descending order when you do this too. All right, so two variations. So that tells me there's either 2 or 0 negative real zeros. So you could have one positive, let's draw a line to separate this, one positive, 2 negative, 0 non-real complex, so that could be the case. Or you could have one positive, 0 negative, and in that case 2 non-real complex. So again, when you go to start trying to figure out, well, what the heck are the zeros for this thing, then you know not to start with the negatives. You know to start with, sorry, not this one. I don't know what I'm saying. I was distracted trying to log into Desmos here so I can get a quick graph for you. But so you know that you have at least one positive, but this is actually not too helpful because you could have 2 negative or not. So it doesn't really narrow it down for you, which is kind of sad. But you know that you can confidently start with the positive ones and try to work with those. All right, so in Desmos, I'm going to kind of cheat a little bit. I'm going to put this in and see what the graph is to get an idea about my zeros, because I want to go through and do the test and see what happens. Okay, plus x minus 10. So when I put that in there, they're telling me that one of my zeros is 1.545. Eek. That sounds gross. So this one ends up with one positive real zero. So that means no negative real zeros. So that means there must be 2 non-real complex zeros in this one. All right. You can always like at home when you're doing your homework, you can always use graphs to give you some clues about what's, or pictures about what's happening. All right, let me do 2 more examples. Let's say you have a problem that asks you to find all of your complex zeros. And you have a function f of x equals x to the 4th plus 29x squared plus 100. There are 0 variations here. So that tells us 0 positives. 0 positive real. Then when you do f of negative x, it actually returns the same looking function. Again, 0 variations. So 0 negative real. But with that x to the 4th, that degree of 4, I know I need to be on the cert hunt for 4 zeros. So apparently they're all going to be non-real. So this problem is actually factorable. I can factor f of x into x squared plus 4 times x squared plus 25. If x squared plus 4 is 0, and x squared equals negative 4, so we get plus or minus 2i there. And if x squared plus 25 is 0, x squared equals negative 25, so we get plus or minus 5i there. So x equals plus or minus 2i and plus or minus 5i for our zeros. So if you went ahead and graphed that, you're not going to see it cross the x-axis on the grid when you put it in. In fact, again, I love playing with Desmos because it's so quick. It's so easy to type everything in, and I can like quickly give you guys an idea about what this graph's going to look like. Although, yeah, it's like you got your axes, and then it's way up here. How's that shape up there? So it floats above the x-axis. I need to zoom in to see a better idea of the actual shape at the base of it where the vertex is, but it's pretty narrow. But that's just, I thought that was an entertaining example, so you might come across those. And then one more. Let's see here. F of x equals x to the 4th minus 8x cubed plus 29x squared minus 66x plus 72. And we want all complex zeros in exact form. Well, for f of x, I see 1, 2, 3, 4 variations. So there can be 4, 2, or 0 positive real. And then for f at negative x, I end up with 0 variations. So 0 negative real. So you could end up with either 4 positive real and 0 non-real, or you could end up with 2 positive real and 2 non-real, or 0 positive real and 4 non-real. So that's the situation. But knowing there's no negatives can narrow things down quite a bit. So let's do that. Let's revisit our f of x and start looking for some zeros. All right, P is 72. We're dealing with 72. So we're dealing with plus or minus 1, plus or minus 2. I'm just listing the factors right now. Plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 24. This is a long one. Plus or minus 36, plus or minus 72. And then for Q, we're focusing on 1, so we have plus or minus 1. Well, keeping in mind, we only need to try positives. Positive reals. So that narrows it way down when you start doing your P over Q, which the Q is being 1, so P over Q, it's either going to be positive or negative of what you've got going on there. But we can only have positive reals, so negative over negative is going to be positive, so all you really need to deal with is positive. Positive 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, 72. So those are some of the ones to try. So we have 1, negative 8, 29, negative 66, 72. You can try some negatives, but they're not going to work. In fact, like I tried a 1 and then I tried 2. I couldn't get either one of those to work, so I went straight to 3. And when I did that, I got here. So that, and then turns out I can try 3 again. And go even further. And then for x squared minus 2x plus 8, I use the quadratic formula. Sorry. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Oh, goodness. All right, so just putting that into quadratic formula. So then I know my zeros are 3 with multiplicity 2, and then 1 plus or minus I square root of 7. I start out with an x to the 4th. Like I had a degree of 4 in that polynomial originally. So it makes sense that I like 3 twice, and then that conjugate pair, because I had all real coefficients. So the non-real complex comes in the pair, the conjugate pair. So I have and then my Descartes rule of signs helped me to realize I didn't need to bother with negatives to try. I could just try positives. So I went through and found that 3 worked. And it turned out 3 worked again. So that multiplicity 2 there. And then the 1 plus or minus I squared root of 7. And if you wanted to write it in a factored form, you could do x minus 3, x minus 3, x minus 1 plus I squared root of 7, x minus 1 minus I squared root of 7. So you could do that. All right, well, I think that pretty much wraps it up for the zeros of polynomial functions. Thank you for sticking it out with me. I know it was long. I ended up using more slides than I thought I was going to. As you might have noticed, those last few slides I had to kind of go back. But this is definitely an important lesson. You're going to be using these skills again in the next lesson when we get into the nitty-gritty of graphing these polynomial functions. So I look forward to seeing you again soon when we do some graphing.